Some of our newest buildings are already falling apart. Meanwhile, silent sentinels from antiquity stand unshaken after thousands of years. This is the undeniable paradox of progress, and it forces a single, urgent question. What ancient knowledge did our ancestors possess that we have somehow lost in our rush to build faster and cheaper? By the end of our journey, you will hold the keys to a forgotten library of material science, one that could redefine how we build our future. We will uncover why Roman concrete thrives in seawater, how Chinese mortar was strengthened with sticky rice, and what secret keeps an iron pillar in Delhi rust-free for over 16 centuries. These are not mere historical footnotes. They are masterclasses in durability, written in stone, metal, and mortar. Each recipe reveals a deeper truth about working with nature rather than against it. So what does it truly mean to build something that lasts? A concrete parking lot can begin to crumble in just 20 short years, its surface a web of fractures under the relentless sun. Yet the dome of the Roman Pantheon, a perfect hemisphere of ancient concrete, has gazed down upon the world for nearly 2,000 years without a single crack in its core structure. This is the paradox that quietly undermines our faith in progress. We assume newer materials are superior, but time delivers a different verdict. The evidence is not in a laboratory report, but in the skyline of history itself. So what fundamental shift occurred? It begins with a question of intent. For the Roman engineer, construction was an act of legacy, a conversation with eternity. Every mix of mortar, every placement of stone, was done with the unwavering belief that this creation must speak to generations unborn. Modern construction, by contrast, often operates under a different master, the tyranny of the immediate, the budget, and the deadline. This philosophical chasm manifests in the very substance of our materials. To understand why the Pantheon endures while our own structures falter, we must look past the surface and into the molecular heart of the material itself. Our investigation starts not with a complex machine, but with a simple, transformative ingredient the Romans pulled from the earth, one that gave their concrete a secret power we are only now beginning to fully comprehend. The secret was hidden in the volcanic hills of Pozzolanic. There, Roman engineers discovered a fine, sandy ash that would become the soul of their empire's most enduring structures. They called it Pozzolana, and when mixed with lime and seawater, it performed a kind of alchemy. Modern Portland cement, the binder in most contemporary concrete, is chemically brittle in the face of salt water. The chlorides attack the steel reinforcement, causing it to rust and expand, which then cracks the concrete from the inside out. Roman concrete, however, had no steel to corrode. Its strength came from a far more elegant and resilient chemical conversation. When Pozzolana met lime and seawater, it began a slow, perpetual reaction. Over decades and centuries, this mixture crystallizes into a rare mineral called aluminous tobamorite. Think of it not as a static glue, but as a living, growing scaffold within the material. This crystalline network does not simply resist seawater, it uses it. The constant flow of minerals through the porous concrete actually encourages more of these strong, interlocking crystals to form. So, while a modern marine pier might be slowly eaten away, a Roman breakwater becomes tougher, more monolithic with every passing wave. This is not mere durability, it is a form of material evolution. Researchers like Marie Jackson have used advanced imaging to watch this process at a microscopic level, revealing a world where cracks are not failures, but opportunities for self-repair. The concrete at the ancient harbor of Caesarea is not just surviving after 2 millennia underwater, it is arguably in better condition today than when it was first poured. The Romans, whether by brilliant intuition or meticulous observation, engineered a material that was in partnership with its environment. They built not against the sea, but with it, creating a legacy that whispers a profound question to our own era of disposable construction. What if our buildings could grow stronger with time rather than weaker? This principle of partnership extended far beyond the volcanic shores of the Mediterranean. To find its next great expression, we must travel across a continent and forward in time, to the monumental stone ribbon of the Great Wall of China. Here, particularly in sections constructed during the Ming Dynasty, the mortar holding the massive bricks together has withstood not just centuries of weathering, but the violent tremors of earthquakes. For generations, the resilience of this mortar was a quiet mystery, its recipe lost to history. Then, researchers made a startling discovery. The secret ingredient was not a rare mineral, but a common meal, a simple porridge made from sticky rice. This humble addition was a stroke of material genius. The key component in sticky rice is a complex carbohydrate called amylopectin. When mixed with slaked lime, this organic soup created a mortar with properties that seem almost magical. Think of amylopectin as a natural polymer, its long, branching chains weaving themselves through the inorganic lime. This acted as a powerful binder, creating a cohesive matrix that was far more resistant to water penetration and physical stress. It slowed down the natural carbonation process, giving the mortar time to develop a dense, almost plastic-like internal structure with incredible compressive strength. The result was a biocomposite material, a perfect synergy between the mineral and the organic. The builders of the Ming Wall did not have modern chemistry labs. Instead, they looked to their own fields and kitchens, harnessing a local agricultural product to solve an engineering challenge. They understood, on an intuitive level, that the sticky substance that made their rice clump together in a pot could also make their mortar cling tenaciously to stone for 1,000 years. This was not a crude folk remedy, but a sophisticated application of material science, one that modern engineers are now trying to replicate with synthetic polymers. The lesson is profound. It suggests that some of the most durable technologies are not extracted from the earth with great force, but cultivated from it with understanding. From the volcanic ash of Italy to the rice paddies of China, a pattern emerges. The ancients did not see materials as inert ingredients to be dominated. They saw them as partners in a dialogue, each with unique properties to be listened to and leveraged. And as we will see, this dialogue reached its most astonishing and perplexing peak not with a flexible mortar, but with a metal that seemingly defies the most relentless law of nature. But perhaps the most dazzling testament to this ancient dialogue with matter is not found in a wall or a harbor, but in the palm of your hand. Deep within the tombs of the pharaohs, alongside golden treasures, archaeologists have recovered small, luminous objects. Scarab beetles, delicate amulets, and intricate tiles, all shimmering with a brilliant, celestial blue that has not dimmed for over 5,000 years. This is Egyptian faience, and it is not a stone, nor a metal, nor a painted ceramic. It is something far more ingenious, a testament to an early mastery of silica that rivals our modern composites. The artisans began with the humblest of ingredients, sand or crushed quartz. They mixed this with a tiny amount of lime and natron, a natural salt, and just enough water to form a paste. This paste could be molded much like clay, but the true magic happened in the fire. When heated, the mixture underwent a process called sintering. Imagine the quartz particles on the surface beginning to soften and fuse together at their edges, creating a porous yet coherent white body. Now here is the stroke of genius. Before firing, the object was coated with a powdered glaze made from copper minerals. As the kiln's heat rose, this glaze would melt into a thin, glassy skin, sealing the sintered core beneath. The copper, interacting with the chemistry of the glaze, produced that unforgettable, stable blue, the color of the Nile and the heavens. This was not a surface paint that could chip or fade. The color was the glaze, and the glaze was an integral protective shell. The result was a material of astonishing permanence. While the painted walls of later eras might flake and lose their vibrance, these faience objects retained their luminous glow through millennia, immune to moisture, resistant to corrosion, and seemingly untouched by time itself. This achievement speaks to a holistic vision of creation where art, science, and spirituality were inseparable. The blue was not merely decorative, it held deep symbolic meaning, representing life, fertility, and the cosmos. The Egyptians did not just want a durable material, they wanted one that could carry meaning into eternity. In faience, they achieved both, crafting a ceramic that glowed with a light that modern plastics and pigments often struggle to match. It is a quiet reminder that ancient innovation was not solely about monumental strength, but also about achieving a perfect, lasting beauty. And this pursuit of perfection, of creating something truly eternal, leads us to the final and most baffling material in our collection, a metal that stands in the open air, daring the elements to do their worst, and has been winning that silent battle for 1,600 years. Standing in the quiet courtyard of the Qut complex in Delhi is a metal column that openly mocks the passage of time. The iron pillar of Delhi rises over 7 meters, a single, seamless shaft of wrought iron forged in the 4th century. For more than 1,600 years, it has endured scorching heat, torrential monsoon rains, and the pollution of a modern megacity, yet its surface remains remarkably smooth, free of the deep, destructive rust that should have consumed it centuries ago. This is not a story of a sheltered relic. It is a monument that has spent its entire life in the open air, defying the most fundamental law of metal: iron wants to rust. So how is this possible? Modern stainless steel relies on chromium to form a protective layer, but this pillar predates that technology by over a millennium. The answer is not in its shelter, but in its very substance. Ancient Indian metalworkers, guided by texts known as the Lohashastra, or the science of metals, achieved something extraordinary through their forging process. They used iron ore with a naturally high phosphorus content and very little sulfur or manganese. When they hammer-forged the pillar, heating and folding the metal repeatedly, they did more than shape it. They created a unique, thin protective film on the surface, a stable compound called Misawhite. Think of this not as a coating applied later, but as a skin that grew from within during its creation. This passive layer acts as a shield. When the first atoms of iron on the surface react with oxygen, they form this stable, dense patina, which then stubbornly resists any further corrosion. It essentially puts up a stop sign, telling the corrosive process that the reaction is complete, sealing the metal beneath. This is a brilliant, empirical feat of passivation, a concept modern science only formally understood in the 20th century. We use similar principles today to protect aluminum and other metals. The pillar stands as a quiet, towering question to our assumptions about progress. Those ancient smiths without electrochemical theory or electron microscopes manipulated the chemistry of their material through fire, hammer, and profound observation. They didn't just make a pillar, they engineered a condition, a state of being that chose permanence. It is a masterpiece not of monumentality, but of molecular diplomacy, a treaty written in iron with the atmosphere itself. And it forces us to wonder, what other profound understandings of the material world have we overlooked in our rush toward the new? The iron pillar is a silent monument to a different way of knowing. To label its creators as merely lucky or primitive is to miss the point entirely. They were masters of a sophisticated, hands-on science, a discipline of deep observation and relentless experimentation that we might call the first true material engineering. They worked without textbooks or chemical formulas. Their laboratory was the forge, the kiln, and the construction site itself. Historians like Pamela Smith refer to this as vernacular science, a profound knowledge system built not in academic institutions, but through generations of artisans speaking directly to the materials of their world. A medieval alchemist seeking the philosopher's stone, or a master mason mixing mortar, shared a fundamental methodology. They would take a local clay, a particular volcanic ash, or an ore from a specific hillside, and through countless trials learn its personality. How did it behave when mixed with rainwater versus spring water? What color did it turn at one temperature versus another? Which aggregate made the mix stronger and which made it crumble? This was science written in the language of fire, fracture, and success. Every recipe was a dialogue with place. The Roman use of Pozzolana was born from the unique geology of Campania. The sticky rice mortar was a direct application of a staple crop. These were not universal, off-the-shelf solutions, but bespoke formulations, perfectly adapted to local conditions and challenges. This stands in stark contrast to our modern industrial paradigm, which often seeks a single, uniform material to be shipped and used anywhere in the world, sometimes with disastrous results when local environments defy the standard. The ancient artisan's goal was not just to make something, but to understand the inherent qualities of their ingredients and coax them into a lasting partnership. They viewed materials as having almost a spirit or a disposition, a perspective that, while not scientific in our terms, led to incredibly scientific results. It fostered a patience and a respect for process that we have largely traded for speed and scale. They knew that true durability could not be rushed, that the secrets of stone and metal were revealed only to those who watched, listened, and learned over a lifetime. This empirical wisdom, passed down through guarded guild secrets and oral tradition, was the invisible framework upon which all these enduring marvels were built. It compels us to ask, in our age of instant data and standardized specs, what profound material truths are we failing to hear because we have stopped listening to the world itself? Deep within the humid embrace of the Central American jungle, another ancient conversation with materials was taking place. The towering temples of the Maya, like those at Capon, were not simply carved from stone. They were meticulously finished with a plaster skin of astonishing resilience. To the untrained eye, it is simply a smooth, white surface, but modern science has peeled back the layers of time to discover a secret within the mix. Mayan plaster was not just durable, it was, in a very real sense, alive. Their recipe began with the familiar base of burnt limestone, but then they introduced a transformative ingredient drawn directly from their environment, the sap of local trees like chucum and geote. This was not a random addition. The organic compounds in these plant extracts acted as natural water repellents, helping the plaster shed the relentless tropical rains. But their true genius was far more dynamic. When microscopic cracks inevitably formed in the plaster over time, environmental humidity would seep in. The organic compounds from the tree sap facilitated a process called bio-mineralization. In essence, they encouraged the lime in the plaster to dissolve slightly and then recrystallize, seamlessly filling those tiny fractures from within. The Maya had engineered a material that could heal its own wounds. This concept of self-healing concrete is one of the most exciting frontiers in modern material science, with researchers spending millions to develop synthetic polymers and bacteria-filled capsules to achieve a similar effect. Yet here, in the archaeological record, is a fully realized version created over 1,000 years ago using the bounty of the forest. This was architecture in true partnership with its place. The Maya did not see the jungle as an obstacle to be cleared, but as a partner to be consulted. By integrating the chemistry of local trees into their built environment, they created a living, responsive building skin that maintained its integrity by working with the very humidity that would normally destroy such a surface. It represents perhaps the most intimate form of the ancient material philosophy we have seen, a seamless fusion of botanical knowledge and architectural ambition that resulted in a structure that could care for itself. This legacy of intelligent, localized adaptation raises a pressing and perhaps uncomfortable question for our own globalized world. If the secret to longevity was found in listening to and leveraging local conditions, what have we lost by standardizing our approach to building everything, everywhere? The philosophy of listening to local materials found its ultimate expression not in a temple or a pillar, but in a vessel built to conquer the most unforgiving environment on Earth, the open North Atlantic. For the Vikings, survival and conquest were not just matters of courage and navigation, but of material ingenuity. Their legendary longships, capable of crossing an ocean, were feats of woodworking, but that wood would have been worthless without a protective secret drawn from the very forests that supplied it. The Vikings mastered two key materials that turned their ships into extensions of their will. The first was a humble gray-green stone. Soapstone, quarried from specific locations, was prized for its remarkable properties. Unlike other stones, it is soft enough to carve but possesses an extraordinary ability to absorb and radiate heat evenly and to withstand sudden temperature changes without cracking. On the deck of a rolling longship in a freezing sea, a soapstone hearth or cooking pot was not a luxury. It was a lifeline, allowing a hot meal to be prepared safely where a ceramic pot would shatter. This was a pragmatic selection, using a material perfectly suited to the thermal violence of their world. But the true guardian of their voyages was not stone, but a sticky, black substance that sealed their destiny. They produced it in astonishing quantities through a process that was chemistry in action. By slowly burning pine wood in a pit covered with turf, they created an oxygen-limited environment, a controlled pyrolysis. This careful, smoldering burn drove off volatile compounds and left behind a thick, viscous resin, pine tar. This tar was the blood of their ships, brushed onto planks and woven into the seams of the hull with animal hair. It created a flexible, waterproof barrier that kept the relentless sea at bay. It preserved the wood from rot, repelled boring worms, and gave the ships their iconic dark silhouette. Think about the sophistication here. This was not a simple campfire. It required an understanding of airflow, temperature control, and feedstock to produce a consistent, high-quality sealant. The durability that enabled a voyage from Scandinavia to Newfoundland was not just in the sleek lines of the hull, but in this derived organic armor. Every longship was a floating testament to a survival-oriented science, one that looked at a pine forest and saw not just timber, but the very glue that would hold an empire of the waves together. Their material world was a closed, intelligent loop, using what their ecosystem provided to protect what they built from it. This deep connection raises a final, pivotal question that brings our journey full circle, from ancient harbors to modern labs. If these disparate cultures from Rome to Scandinavia all achieved such legendary durability by working in harmony with their local environments, why did this profound wisdom ever fade from our collective memory? The ultimate test of a material is not merely weathering the elements, but withstanding the focused fury of human ambition. For over 1,000 years, the fate of an empire rested upon a single, staggering line of defense, the Theodosian walls of Constantinople. These were not simple barriers of stone, but a layered, intelligent system engineered to do one thing perfectly: to say no. And they said it for centuries, not through a single wonder substance, but through a brilliant orchestration of ordinary materials. The core of the walls was a thick mix of rubble and mortar, a practical and economical fill, but its true genius was revealed in the alternating skin that faced the world, bands of precisely cut limestone seamlessly interwoven with 5 courses of red brick. This pattern, known as Opus Mixtum, was a masterclass in material synergy. Each component played a distinct, vital role. The massive stone blocks provided immense compressive strength and sheer mass, a formidable obstacle to any battering ram. But stone is rigid and can crack under repeated, focused impact. This is where the bricks came in. Their smaller, modular nature and the mortar joints between them created a degree of flexibility, a subtle give that could absorb and dissipate the energy of a siege engine's blow, like a boxer rolling with a punch. Furthermore, this composite skin was a brilliant hydrological system. The different materials expanded and contracted at different rates with temperature changes, preventing large, catastrophic cracks from forming. And the porous mortar and brick acted like a capillary network, drawing moisture out of the core and allowing it to evaporate, keeping the structural heart of the wall dry and stable. The builders understood that durability was not a property of one substance, but an emergent behavior born from the careful relationship between many. They were systems thinkers, engineering not just a wall, but an entire defensive ecosystem in stone and clay. It was a resilience born of diversity, where the interaction of textures, porosities, and strengths created a whole of legendary endurance. This layered philosophy invites a deeper reflection. Perhaps the greatest ancient material of all was not a concrete or a metal, but an idea, a way of thinking about the built world as a complex, responsive partner rather than a passive object. The true magic of these ancient materials unfolds at a scale invisible to the human eye. To grasp why they endure, we need to listen to the quiet, centuries-long conversation happening within their very substance. Think of modern Portland cement. It sets through a rapid, almost frantic chemical reaction called hydration. Water quickly binds with the cement compounds, forming a rigid matrix that gains strength in days or weeks. But this speed comes at a cost. The process can create internal stresses and leave behind microscopic voids and weaknesses, like a hastily assembled puzzle with gaps between the pieces. When environmental stress arrives, these tiny flaws can become the starting points for larger cracks, a chain reaction of failure. Now contrast this with the patient alchemy of a Roman pozzolanic mix. Here, the key ingredients, silica and alumina from volcanic ash, do not react immediately. They are slowly awakened by the presence of lime and water, beginning a gradual, persistent dialogue that can last for decades. Over this immense timescale, they form intricate, interlocking crystals, like a mineral tapestry weaving itself tighter and stronger with every passing year. This creates a far denser, more cohesive internal architecture, one that distributes stress evenly and leaves fewer weak points for failure to begin. But the chemistry of longevity does not stop there. Consider a simple, traditional lime mortar. Its hardening process is a beautiful exchange with the atmosphere itself. As it cures, it slowly absorbs carbon dioxide from the air, a process called carbonation. This transforms the soft lime into solid limestone again, essentially turning the mortar back into a rock, molecule by molecule. This is not a reaction that finishes in a month. It can continue gently for centuries, a slow, steady increase in strength and density that modern accelerated mixes never experience. These ancient chemical pathways are not faster or stronger in the short term. They are smarter. They prioritize long-term stability and resilience over immediate set time. They build a material world that is adaptable, that can settle and shift and even self-repair because its chemical story is still being written. Our modern materials often tell their entire story in the first few weeks, leaving them static and brittle for the long plot of history. The lesson from the laboratory of the past is profound. Sometimes true strength is not about how fast you can set, but how wisely you can grow. This sophisticated dance with moisture found one of its most elegant expressions far to the east on the gleaming white walls of Heimji Castle. In Japan's humid climate, where wood is king but decay is a constant threat, artisans developed a plaster that did not simply seal a building but allowed it to breathe. This material, known as Shikkui, is a masterclass in balanced material science. Its recipe reads like a dialogue with the local environment. Slaked lime formed the base, providing strength and alkalinity to deter insects and mold. But the transformative ingredients came from the sea and the field. Sticky glue extracted from a seaweed called fonori was added as a natural binder, giving the mix plasticity and a subtle, resilient grip. Then finely chopped hemp fibers were kneaded in, acting as a microscopic reinforcement network to control cracking. The result was a plaster with a seemingly paradoxical set of abilities. Its surface was hard and smooth, shedding driving rain like a duck's back. Yet, at a microscopic level, it remained vapor permeable. Moisture vapor generated inside the living wooden structure could slowly migrate out through the plaster, preventing the trapped dampness that leads to dry rot and structural failure. This balance between water resistance and breathability is a central, often costly, challenge in modern construction, typically solved with layered synthetic membranes and complex wall assemblies. Shikkui achieved it in a single, cohesive layer using entirely natural, locally sourced materials. It was not just a coating, it was a responsive environmental filter. The artisans who mixed it understood, on a profound empirical level, that a building is not a sealed box, but a living system that must exchange with the air around it to survive. In the flawless, luminous walls of a centuries-old temple, we see not just aesthetic beauty, but a deep, intuitive grasp of building physics, a silent guardian ensuring the wood within could endure for generations. Beneath the sun-scorched deserts of ancient Persia, a hidden network of veins carried the lifeblood of civilization. These were the qanats, subterranean aqueducts that channeled water from distant mountain aquifers to arid valleys and cities, all by the gentle, unceasing pull of gravity. For over 3,000 years, these tunnels have flowed without a single pump or electric motor, a testament to an infrastructure so intelligently conceived and durably built that many remain in use today. Their endurance, however, did not rely on the genius of their slope alone. It depended on the silent, unseen guardian that lined every meter of their dark passage, a specially formulated mortar that held the desert at bay. Working deep underground presented a unique set of material challenges. The lining had to be pliable enough for artisans to apply by torchlight in cramped, humid tunnels, yet it had to set reliably without the rapid drying breeze of the open air. Once cured, it faced a perpetual trial, holding back immense soil pressure while being constantly bathed in flowing water. Any failure meant catastrophic collapse or the precious water seeping away into the thirsty earth. The Persian engineer's answer was often a material called sarouj. Much like Roman concrete, sarouj was a hydraulic mortar, meaning it could set and remain stable even underwater. Its recipe was a localized alchemy, typically combining lime with volcanic ash or even burned, crushed ceramics. This mixture created a paste that, when smeared onto the tunnel walls, initiated a slow, steady chemical reaction with the mineral-rich groundwater itself. The result was a lining that became integrally bonded to the surrounding geology, a seamless, waterproof shell that grew tougher with time. This was geotechnical mastery of the highest order. The lining did more than just contain water. It managed the entire relationship between the tunnel and the earth. It stabilized the walls against shifting soils, prevented erosion from the constant flow, and created a smooth channel that minimized friction and maintained the water's vital momentum over astonishing distances, sometimes spanning 50 miles or more. In the absolute darkness, these artisans engineered a material dialogue between rock, water, and chemistry, building not a structure upon the land, but a resilient artery within it. The qanat did not conquer the desert, it negotiated with it, using a whispered language of mortar and patience to draw life from stone. This humble lining sustained empires, turning barren basins into blooming gardens, and it poses a quiet, profound challenge to our own era of visible, above-ground infrastructure. What does it mean to build not on the landscape, but in conscientious conversation with it, creating systems so harmonious and durable they become invisible, working flawlessly for millennia? High in the stone ribs of a Gothic cathedral, light is not merely admitted, it is transformed. The great rose windows and towering lancets of places like Chartres Cathedral are not just architecture, they are alchemy, turning sunlight into a narrative of ruby, sapphire, and amethyst that has blazed undimmed for more than 800 years. While the stonework around them has been eroded by centuries of rain and industrial pollution, these panes of colored glass have not just survived, they have retained a luminous intensity that modern glass often struggles to match. This is not a paradox of preservation, but a testament to a forgotten recipe for radiance. Medieval glassmakers worked with a fundamental formula of potash, lime, and silica. The potash, derived from burned hardwood ash, gave the glass a different chemical personality than the soda-lime glass that became standard later. This potash-lime-silica glass was inherently more stable and resistant to environmental attack. But the true magic was in the color, a magic drawn directly from the earth. Artisans introduced metallic oxides into the molten mix with the precision of a master painter. Cobalt produced deep, celestial blues. Copper, carefully controlled, could yield a rich ruby red. Manganese gave regal purples and could also be used to decolorize unwanted tints. This was not a surface stain or a painted layer. It was color born within the very substance of the glass, an integral part of its identity. And here lies a crucial insight into its longevity. Medieval glass was not perfect by modern standards. Its sheets were often thicker at the bottom than the top, filled with tiny bubbles, streaks, and a subtle, wavy texture. We might see these as flaws, but time reveals them as features. This uneven surface and varied thickness created a complex interface with the weather. Over centuries, a slow, gentle weathering occurs on the outermost layer. This process, far from destroying the glass, forms a thin, protective patina, a kind of mineralized skin that actually shields the vibrant colored core beneath from further degradation. The window develops a gentle, silky iridescence, a bloom that softens the light without stealing its color. Modern float glass, by contrast, is engineered for flawless clarity and perfect flatness. Yet this very perfection can make it more vulnerable, as pollutants and moisture attack a uniform surface with uniform effect. The medieval window, with its organic imperfections and deeply integrated chemistry, weathers gracefully as a stone in a river becomes smooth. Its endurance is a lesson in the virtue of depth over superficial perfection. The glassmakers did not just make a transparent barrier, they engineered a luminous, colored stone meant to converse with light for a millennium, proving that sometimes the most brilliant legacy is one that learns to wear the centuries like a crown. The brilliance of these ancient recipes is meaningless without the wisdom of their preparation. A master chef knows the finest ingredients can be ruined by haste, and so too did the ancient mason. For materials like lime mortar, the secret was not merely in the quarry, but in the quiet, patient weeks and months that followed. The transformation began with quicklime, a caustic powder produced by roasting limestone in a kiln. Modern construction often slakes this material quickly, adding just enough water to achieve a dry hydrate for immediate use. But the ancient approach was profoundly different. They would submerge the quicklime in a pit of water, and then they would wait. They might leave it to mature for a season, a year, or even longer. This extended slaking was not idle time, it was a critical phase of material evolution. The slow, complete hydration allowed the lime particles to break down into an ultra-fine, silky putty. This extended process encouraged the growth of beneficial mineral precursors and gave the lime a buttery plasticity and a far greater surface area for bonding. Think of it as the difference between hastily mixing flour and water for a paste versus carefully developing a sourdough starter over months. One is merely adhesive, the other develops a complex, living structure. This aged lime putty was the heart of a mortar that could breathe, flex, and self-heal micro-cracks over centuries, but the artisan's patience did not end at the mixing pit. Once the mortar was laid between stones, the curing process began, and it was treated with similar reverence. They understood that rapid drying was the enemy of strength. A mortar that loses its moisture too quickly becomes brittle, its crystalline structure weak and incomplete, so they would carefully keep the new masonry damp, covering it with wet straw, burlap, or animal skins, and misting it regularly for weeks or even months. This slow, controlled curing allowed the carbonation process to happen evenly and thoroughly from the inside out, transforming the soft lime back into a dense, resilient stone. Time itself was not a constraint to be minimized. It was the most vital ingredient in the mix, a silent partner in the chemical conversation. In our world of overnight cures and 24-hour assembly, this philosophy feels almost alien. We have traded the deep, enduring strength born of patience for the immediate utility of speed. Yet, a new generation of material scientists is looking back, recognizing the genius in this slow alchemy. Innovations like geopolymer concretes and advanced lime formulations are, in essence, a high-tech return to this ancient principle, seeking strength not from faster reactions, but from smarter, more patient molecular architectures. It begs a reflective question about our own values. In an age obsessed with instant results, what profound qualities are we sacrificing by refusing to let our creations simply take the time they need to become truly permanent? Granite blocks weighing more than 20 tons are fitted together so tightly that a razor blade cannot slip between them. At the heart of the Andes, the Incas engineered a different kind of permanence, one that did not rely on mixing a perfect mortar, but on achieving a perfect silence. Their ashlar masonry, seen in the breathtaking terraces and temples of Machu Picchu, is a geological puzzle solved with stone alone. Here, durability was not created in a kiln or a forge, but discovered in the mountain itself through an intimate, almost spiritual understanding of the living rock. The Incas did not see a boulder as an obstacle, but as a potential partner, its form and fracture lines holding the blueprint for its future shape. They worked primarily with hard, dense stones like granite and andesite, materials chosen not for ease of cutting, but for their incredible resistance to the relentless forces of their environment. The true genius, however, lies not in the stone they chose, but in the conversation they initiated between each massive piece. Using stone hammers, sand, and water for abrasion, and an immense reserve of patience, they shaped each block with astonishing precision. The goal was not a flat surface, but a complex, three-dimensional interface. Many joints are subtly convex or concave, locking together like a stone jigsaw puzzle. This meticulous fitting created a bond so intimate that it eliminated the need for any binding mortar whatsoever. The structure became a single, cohesive entity. This approach speaks to a profound insight into how forces move through the Earth. The Andes are one of the most seismically active regions on the planet. A rigid, mortar-bound wall would crack and collapse under the shearing forces of an earthquake. But an Inca wall with its intricate, interlocking joints behaves differently. When the ground shakes, the stones in an Inca wall can minutely shift and settle against one another, distributing the seismic energy across the entire structure before settling back into place, often even more tightly than before. They built not for rigidity, but for resilient flexibility, allowing the architecture to dance with the mountain rather than fight against it. This represents perhaps the ultimate expression of the ancient material philosophy. The Incas achieved legendary durability not by inventing a new substance, but by listening so deeply to the one, their world provided that they could hear the perfect way for it to fit together. Their legacy is a quiet testament to the power of selection, precision, and a harmonious geometry written in stone. Long before the first oil well was drilled, the earth itself offered up a sticky, black promise of permanence. In the sun-baked floodplains between the Tigris and Euphrates rivers, Mesopotamian builders encountered natural seeps of bitumen, a thick, viscous petroleum tar that welled up from the ground. To them, this was not a curiosity, it was a foundational technology. From the great ziggurats of Ur to the legendary walls of Babylon, bitumen became the silent guardian against a relentless enemy, water. They used it with brilliant practicality, brushing it onto reed mats to line irrigation canals and waterproof the foundations of temples. They mixed it with sand and minerals to create a durable, flexible mortar for setting bricks, and they sealed the joints of elaborate bath complexes and drainage systems, ensuring the lifeblood of their civilization flowed without leaking away into the thirsty soil. This was humanity's first large-scale partnership with a hydrocarbon, a foray into polymer chemistry millennia before the word was invented. The bitumen acted as both an adhesive and a preservative, its plastic nature allowing the masonry to settle and shift slightly under load or thermal expansion without developing catastrophic cracks. Think of it as giving the rigid bricks a degree of forgiveness, a subtle flexibility that prevented failure. Of course, this early polymer had its limits. Under the scorching Mesopotamian sun, it could soften, and in rare cold snaps it might become brittle. Yet its advantages were so profound that its use spanned thousands of years. This material choice reveals a pattern we have seen from Rome to Persia, a pattern of localized genius. They did not import a solution, they looked at what their specific landscape provided, and in the seeping tar pits, they saw the answer to their most pressing environmental challenge. Today, we see echoes of this ancient innovation in every mile of modern asphalt roadway, and in the polymer fibers we add to concrete to control cracking. We are still pursuing that same ideal of flexible, waterproof durability, but with synthetic chemicals instead of a gift from the earth. The bitumen of Mesopotamia invites a final, overarching reflection, one that ties every story from our journey together. From volcanic ash to sticky rice, from iron pillars to self-healing plasters, a unified philosophy emerges, one that modern construction has largely abandoned in its quest for uniformity and speed. What if the ultimate ancient material was not a substance at all, but a way of thinking? That same principle of listening to the earth found a more humble, yet equally revolutionary, expression in the hands of Greek and Roman artisans. While marble might capture the glory and concrete the structural genius, the true workhorse of their built world was something far more common: clay transformed by fire. Terracotta, literally baked earth, was the silent revolution that tamed the elements within the home and the city. The magic was not in the raw material, but in the alchemy of the kiln. A lump of soft, malleable clay, when subjected to the intense, controlled heat of a pottery furnace, undergoes a fundamental change. The water is driven off, and the silica particles within the clay begin to fuse together in a process called vitrification. This creates a glassy, interlocking matrix that turns a substance vulnerable to rain and frost into a hard, ceramic shell, impervious to water and remarkably resistant to both fire and freezing temperatures. This was not a decorative afterthought, it was foundational technology. The Greeks perfected beautiful, overlapping roof tiles that efficiently shed water, protecting the precious wooden structures beneath for centuries. But the Romans took this fired clay revolution to an astonishing level of systemic engineering. They mass-produced terracotta in standardized modular forms. They crafted intricate water pipes ensuring clean supply and sanitation, and they engineered one of the ancient world's great comforts, the hypocaust heating system. Beneath the floors of bathhouses and villas, A network of hollow terracotta tubes, called tubuli, would be stacked to create pillars. Hot air and smoke from a furnace would circulate through these cavities, gently warming the floors and walls above without any soot or fumes entering the living space. This was central heating, powered by fire and built from baked earth. Perhaps even more cleverly, Roman builders used curved terracotta tiles as permanent formwork for their concrete vaults. They would lay these lightweight, interlocking tiles in an arch, and then pour the wet concrete directly over them. The tiles provided the initial shape, became a bonded part of the final structure, and created a smooth, finished ceiling surface all in one step. The durability of these systems speaks to a mastery of kiln technology. To achieve consistent vitrification across an empire, Roman kilns had to reach and maintain high temperatures uniformly, a testament to sophisticated airflow design and fuel management. The result was a material that was durable, modular, reusable, and incredibly versatile. A broken tile could be crushed and used as aggregate. A cracked pipe segment could be repurposed. This was a circular economy in clay long before the term existed. When we look at a modern brick or a ceramic roof tile, we are seeing the direct descendant of this ancient fired clay revolution, a testament to the enduring power of taking the most common substance underfoot and, with fire and wisdom, turning it into a shield for civilization itself. This quiet conversation with the earth carried a hidden benefit, one we are only now recognizing as vital. Ancient building practices were inherently sustainable, not by design but by necessity. Every material we have explored, from Roman pozzolana to Mayan tree sap, shared a common trait: it came from right next door. The concept of embodied energy, the total carbon cost of extracting, processing, and transporting a material, was kept astonishingly low. Transporting a 50-ton granite block or a shipload of lime across an empire was a monumental, rare undertaking. Instead, builders looked to their immediate landscape, their local volcano, their riverbed sands, their own rice harvest. This created a profound regionalism in architecture, where the very substance of a building told the story of its place. Furthermore, these structures existed within a practical, unspoken circular economy. When an older building fell out of use, it was not seen as waste but as a quarry. Its stones were carefully dismantled and reused, its metals melted down, its timbers repurposed. The Colosseum in Rome, for instance, served as a convenient source of pre-cut travertine for centuries of later construction. This was recycling on a grand, pragmatic scale, a continuous loop where materials lived multiple lives across millennia. Contrast this with the modern life cycle of a ubiquitous material like Portland cement. Its production is one of the single largest industrial sources of carbon dioxide on the planet. The reason lies in a fundamental, energy-intensive step: the calcination of limestone. To make cement clinker, crushed limestone must be heated in a kiln to around 2,700 degrees Fahrenheit. This process drives the carbon out of the stone itself, releasing it directly into the atmosphere as CO2 before the material can ever be mixed into concrete. It is a linear, extractive, and carbon-heavy process from the very start. The ancient paradigm points toward a different path, one of regional material loops and intelligent, low-carbon recipes. It suggests that durability and sustainability are not separate goals, but two sides of the same coin. A material that lasts 1,000 years does not need to be replaced, and one sourced from your own backyard requires no transcontinental shipping. This is not a call to abandon modern technology, but to be inspired by an older, more rooted wisdom. As we urgently seek to decarbonize our world, the most relevant innovation for the future of construction might not be a new synthetic polymer, but a return to an ancient principle, building from what the local earth provides and building it to last for good. The philosophy of resilience found its most domestic and ingenious form not in palaces or temples, but in the everyday homes of medieval Northern Europe. In the half-timbered houses that still line old village streets, the spaces between the sturdy oak frames were filled with a humble, earthen composite known as wattle and daub. At first glance, its ingredients seem almost laughably primitive, a simple mix of clay, sand, animal dung, and chopped straw. Individually, these are materials with no real structural promise. Yet, in the hands of a medieval builder, they were combined into a wall system of remarkable intelligence and durability. This was not a material that sought to dominate its environment with sheer mass, but one that negotiated with it through clever, layered design. The process began with a woven lattice of flexible wooden strips, the wattle, creating a three-dimensional canvas. Onto this, the daub was pressed and smoothed. Each component played a critical, synergistic role. The clay acted as the binder, the basic matrix holding everything together. The sand reduced shrinkage and cracking as the mix dried. The chopped straw, however, was the secret reinforcement. Its long fibers distributed stresses throughout the clay matrix, providing tensile strength, much like the steel or synthetic fibers we add to modern concrete to prevent it from shattering under tension. The inclusion of animal dung, often from cows or horses, is particularly fascinating. While its exact role is debated, it likely contributed water-resistant oils and acted as a binding agent, its organic compounds helping to plasticize the mix and improve its workability and cohesion. The resulting wall was a masterpiece of passive performance. It was remarkably lightweight, putting minimal load on the timber frame, yet it provided excellent thermal mass, slowly absorbing heat from a fireplace and releasing it throughout the night. Crucially, it was breathable. Unlike a modern vapor barrier, the porous daub allowed moisture vapor from daily life, cooking and breathing, to pass through the wall and dissipate, preventing the condensation and rot that can plague sealed modern structures. This breathing quality regulated indoor humidity, creating a healthier, more comfortable living environment. Its durability came from a philosophy of resilience, not invulnerability. A daub wall could be dented or cracked by a heavy impact, but it was also easily and locally repaired. A homeowner could simply mix a new batch from materials at hand and patch the damage, a continuous cycle of maintenance that kept the building alive for generations. The strength of wattle and daub was never in the daub alone, but in its perfect integration within a larger system, the flexible timber frame that could sway and settle, and the repairable, breathable infill that adapted with it. This was sustainability and resilience built from the ground up, using what the local farm and field provided to create a shelter that worked in gentle, intelligent harmony with the rhythms of daily life and the passing centuries. Yet for all its clever design, even the most ingenious material system can conceal a hidden flaw. This brings us to a final, sobering case study, one that forces us to confront a crucial distinction between what lasts and what is truly good. The Romans were master hydraulic engineers, and their quest for a durable conduit for water led them to a metal that seemed perfect in every way but one. They turned to lead. In Latin, these water pipes were called fistulae, and from a purely engineering standpoint, lead was a marvel. It is incredibly malleable, able to be hammered into thin sheets and bent into continuous runs with relative ease. It melts at a low temperature, so it could be cast into standardized shapes and joined with simple soldered seams. Most importantly for a water pipe, lead is highly resistant to corrosion from many types of water. It forms a stable, protective patina on its inner surface that prevents pitting and degradation. Some of these lead pipes laid down in the 1st century remained functionally intact, still channeling water for 500 years or more. From a narrow perspective of material longevity, ignoring all other factors, it was a triumph. It was a seemingly permanent solution to the vital challenge of moving a vital resource. But we now know the tragic cost of that permanence. The very stability that made lead so durable in the pipe also made it a silent, leaching poison in the water. The Romans themselves noted certain health issues that modern science links to lead exposure, though they did not make the causal connection we understand today. This example stands as a powerful, necessary counterpoint to every story of ancient material genius. It serves as a critical reminder that durability alone is an incomplete measure of a material's worth. The Romans solved for permanence and workability, but they lacked the framework to evaluate the full life cycle impact of their choice, the effect on the very people the system was built to serve. It underscores a principle that feels profoundly modern, yet is timelessly true. A truly successful material must be judged not just by how long it stands against the elements, but by how harmoniously it exists within the entire web of life it touches. The legacy of the fistulae challenges us to look beyond the impressive lifespan of a substance and ask a deeper set of questions. What are the unseen trade-offs? Who bears the cost of its permanence? It is a cautionary tale written in metal, reminding us that the most enduring innovation is one that sustains both the structure and the society it shelters. The silent wisdom of these ancient materials could have remained locked in stone and mortar forever. Unlocking it requires a new kind of archaeology, one that peers not into tombs but into the atomic heart of matter itself. Today, the secrets of the Pantheon's concrete or the Ming Wall's mortar are not found in scrolls, but in laboratories equipped with electron microscopes and particle accelerators. Scientists are becoming material detectives, using tools like X-ray diffraction and spectroscopy to perform a kind of reverse engineering at the nanoscale. Imagine taking a tiny core sample, drilled from a 2,000-year-old Roman breakwater submerged in the Bay of Naples, and placing it under a beam of intense X-rays. The resulting diffraction pattern is not a blur. It is a fingerprint, a unique signature that reveals the exact crystalline structure within. This is how researchers like those at the University of Utah confirmed the presence of aluminous tobamorite, the miracle mineral that grows in seawater. They are mapping, atom by atom, the intricate architecture that gives these materials their legendary strength. Similarly, a fragment of mortar from the Great Wall, when analyzed with infrared spectroscopy, can reveal the chemical ghosts of its organic past, the long-chain carbohydrates from sticky rice that still influence its properties after centuries. This work transcends traditional archaeology. It is a fusion of history and cutting-edge materials science, where a shard of pottery or a sliver of metal becomes a priceless dataset. The goal is no longer just to understand the past, but to borrow from it. Around the world, research teams are actively attempting to replicate these ancient formulas under modern, controlled conditions. They are creating Roman-inspired concrete mixes, substituting modern industrial byproducts like fly ash for volcanic pozzolana, and testing their performance in simulated marine environments. Others are developing new bio-based mortars, inspired by the Maya and the Chinese, using plant extracts to create self-healing or ultra-resilient composites. This is more than historical curiosity. It is a pragmatic search for solutions. The ancient world, by necessity, mastered low-carbon, locally sourced, and incredibly durable material science. Our modern world desperately needs all three. By decoding these recipes, we are not simply copying the past, we are learning its underlying principles, its philosophy of working with natural chemistry rather than forcing a reaction. We are bridging a gap of 2 millennia, not to live in the past, but to build a more resilient future with the enduring wisdom it left behind. The desert does not forgive, but it can reveal a different kind of strength. In the vast, sun-bleached silence of Egypt, far from the pharaoh's tombs, another community was writing its legacy in stone and mortar. From the 4th century onward, Coptic monks retreated into the wilderness, building monastic fortresses of faith like the monastery of Saint Anthony. Their challenge was not the sea or the earthquake, but a relentless, desiccating environment of scorching days, freezing nights, and sand-scouring winds. Yet their structures stand, a testament to a mortar recipe fine-tuned for a world without water. The monks used a lime-based mortar, but its genius was in its specific, local additions. They often mixed in the abundant desert sand, its unique mineralogy contributing to the mix. More strikingly, they sometimes incorporated crushed pottery sherds, a technique known as coxiopsto. These fragments of fired clay are not just filler, they are chemically active. The firing process gives them a weak pozzolanic character, meaning they can slowly react with lime to form additional binding compounds, much like the volcanic ash used by the Romans, but born from their own broken vessels. This was sustainability in its purest form, turning waste into a building material. But the true architect of this mortar's durability was the climate itself. In the hyper-arid desert, the curing process became an exercise in extreme patience. With almost no liquid water to drive rapid reactions, the carbonation process, where lime absorbs carbon dioxide from the air to harden, occurred with glacial slowness. This allowed for the formation of an exceptionally dense, fine-grained, and stable crystalline matrix. There was no rushing, no internal stress from uneven drying. The mortar simply became stone again at the desert's own deliberate pace, resulting in a surface so hard and glassy it could resist over 1,000 years of thermal expansion, contraction, and abrasive wind-blown sand. This Coptic innovation is a masterclass in contextual adaptation. It proves these ancient builders were not following a single, rigid recipe from a manual. They possessed a flexible toolkit of principles. They understood the core chemistry of lime, and then they looked at their immediate world, asking what local material could enhance it, and how their specific climate could be leveraged, not fought against. In the wetlands, they sought water resistance; in the seismic zones, flexibility; and in the desert, they harnessed aridity itself to forge a different kind of permanence. Their legacy is a quiet reminder that the most durable solution is often not a universal one, but the one born from a deep, attentive conversation with a specific place. A cathedral was never just a building. It was a prayer rendered in stone, a collective aspiration reaching toward the heavens. This spiritual dimension infused every stage of its creation, transforming the act of construction from a technical task into a sacred covenant with eternity. The materials themselves were treated with a reverence we rarely afford to modern concrete or steel. Stone was not merely quarried, it was selected with intention, often from a specific, hallowed site believed to imbue it with strength. The mixing of mortar could be accompanied by blessings, and the laying of a cornerstone was a profound communal ceremony. This ritual care was not superstition, it was a powerful cultural mechanism that enforced quality. It guaranteed that time, the most crucial ingredient in any durable material, was given freely and generously. The master mason operated within this sacred framework. He was more than a technician, he was a link in an unbroken chain of knowledge, a custodian of secrets passed from mentor to apprentice over generations. His personal reputation and spiritual standing were tied to the integrity of his work, for he was building not for a client, but for God and for the countless generations who would worship within those walls. This intangible belief in eternal purpose governed every practical choice. It justified the decades spent carving a single portal, the centuries required to complete the vaulting. It mandated the use of the finest, most enduring materials available, regardless of immediate cost, because the value was measured in lifetimes, not quarterly reports. Contrast this with the prevailing model of modern construction, which is framed almost entirely within an economic calculus. The primary questions are of budget, timeline, and return on investment. The driving force is often efficiency and speed, not legacy. In this system, the cultural layer of meaning, the belief that a structure should serve as a gift to the future, is frequently absent. We have perfected the science of building quickly, but we have neglected the art of building forever. Perhaps then, the most vital ingredient we have lost is not a particular volcanic ash or a tree resin, but a sense of profound responsibility to those who will come after us. Recovering a philosophy of permanence, a cultural commitment to legacy, may be just as essential to creating enduring structures as rediscovering any ancient material recipe. It asks us to view our buildings not as disposable assets, but as future ancestors, silent witnesses to the care or the carelessness of our own age. The earth does not just provide stone, it sometimes offers a material that builds itself. Across the vast plains of West Africa, a unique geological process created a foundation for architecture that was both humble and profound. Builders there worked with laterite, a soft, iron-rich clay that hides a remarkable secret. When first cut from the ground, it can be shaped easily with simple tools, almost like a dense red butter. But left exposed to the sun and air, it undergoes an irreversible transformation. The moisture within evaporates, and the abundant iron and aluminum oxides inside begin to precipitate out, crystallizing and binding the particles together into a hard, durable stone. This is natural cementation in its purest form, a building block that cures itself. No kiln was needed, no complex mortar recipe required. The landscape had already done the chemistry over millennia of weathering. The builder's genius lay in recognizing this latent potential and harnessing its timeline. They would quarry the laterite into massive blocks during the wet season when it was soft, then stack them and allow the dry season to slowly perform its alchemy, turning the entire structure to stone. The Grand Mosque of Djenné, with its iconic, towering facade and projecting timbers, is the most famous example of this dialogue with the earth. Its very substance is the iron-red soil of the region, baked solid by the sun and the wind. This represents perhaps the ultimate expression of local adaptation we have seen. It is architecture of almost zero processing, where the act of building is a form of guided crystallization, a partnership with a geological process already in motion. The material required no import, no fuel-intensive firing, and at the end of its immense lifespan, it could simply erode back into the landscape from which it came, completing a perfect, silent cycle. Laterite asks us to reconsider the very definition of a building material. It suggests that the most enduring structures might not be those we impose upon a place, but those we patiently allow a place to reveal. Stone could reach for the heavens, but it could not hold hands. The soaring vaults and delicate tracery of a Gothic cathedral pushed masonry to its absolute limit, creating breathtaking spans of light and space. Yet this architectural ambition revealed a fundamental weakness in the material itself. Stone is magnificent under compression, bearing immense weight downward. But it possesses almost no tensile strength, the ability to resist being pulled apart. The outward thrust of a vault or the lateral force of a high wind threatened to push the walls outward and send the entire dream collapsing inward. The medieval mason's ingenious solution was to introduce a silent partner into the stone choir, one that could whisper strength where stone could only shout mass. They turned to iron. In the shadows of the triforium, embedded deep within the joints of towering buttresses, they placed iron bars as ties, stretching like hidden tendons across the nave to bind the opposing walls together, countering the vault's thrust with pure, unyielding tension. They forged massive iron clamps, often shaped like a C or a staple, to lock adjacent stones together, transforming a stack of blocks into a unified beam. And they used iron dowels, pins driven through precisely drilled holes to prevent sliding and shifting in key locations. This was not a crude addition, but a sophisticated, early form of composite construction. They were creating a hybrid material system, leveraging the compressive strength of stone and the tensile strength of iron in a brilliant, empirical partnership. But these master builders were not naive. They understood the fundamental flaw in their iron ally, a flaw the iron pillar of Delhi had miraculously avoided. They knew that unprotected iron, when exposed to moisture and air, would rust, and rust does not just decay, it expands with a force so potent it can split granite. To place an expanding metal inside a rigid stone shell was to plant a seed of future destruction, so they engineered protections. In some of the most forward-thinking applications, they sheathed the iron in lead, creating a waterproof barrier that isolated the metal from the elements. In other cases, they placed the iron ties in open channels or boxes within the masonry, not hidden forever but accessible. This was a revelation. It was a philosophy of design that anticipated failure and planned for intervention. These channels were inspection ports, maintenance hatches built into the fabric of the cathedral itself. They acknowledged that even the most durable systems are not immortal, that they exist in time and require stewardship. It was a pragmatic admission that care is a continuous responsibility, not a one-time act. This medieval approach to iron speaks to a humility and a foresight that feels strikingly modern. It represents an early chapter in the story of intelligent material design, where the goal is not a perfect, maintenance-free object, but a resilient, repairable system. They built with the understanding that their work would need to be touched, inspected, and cared for by generations yet unborn, weaving the necessity of future hands into the very blueprint of their stone prayers. Even with our best laboratories and electron microscopes, we cannot simply photocopy the past. The challenge of recreating these ancient materials is not merely a chemical puzzle. It is a profound cultural and economic dilemma. The first hurdle is one of place. A Roman engineer used pozzolana from a specific volcanic field in Pozzolanic, ash with a unique mineral fingerprint shaped by that region's geological history. We can find similar volcanic materials elsewhere, but they are never quite the same. It is like trying to replicate a grandmother's legendary soup recipe when her secret herb grew only in her own backyard. The specific synergy between that local earth, the local lime, and even the local water created a performance that is chemically tied to its origin. We can approximate the recipe, but we cannot duplicate the exact ingredients because the earth itself is not a standardized supplier. Then there is the tyranny of time, or rather, our modern refusal to grant it. The most potent ingredient in many ancient materials was patience, a resource our current systems are engineered to minimize. A medieval mason could let his lime putty mature for a year in a pit. A modern construction project is budgeted down to the hour. The slow, gentle carbonation that gives traditional lime mortar its resilient, self-healing character happens over seasons, not the 28-day cure cycle that defines modern concrete strength tests. Our entire regulatory and economic framework is built around predictable, quantifiable results on a spreadsheet measured in weeks. How do you put a price on a strength that increases for a century? How do you write a building code for a material that achieves its best performance long after the original engineers have passed? We demand certainty by Friday, but the ancient world traded immediate certainty for proven longevity over 1,000 Fridays. This leads to the silent, irreplicable advantage every ancient structure possesses: centuries of benign aging. A Roman concrete breakwater did not reach its current indestructible state in a decade. It spent 2,000 years in a gentle chemical conversation with seawater, slowly growing its internal crystalline armor. The protective patina on the iron pillar of Delhi, or the silky skin on medieval glass, are records of environmental dialogue we cannot fast-forward in a lab. We can create a new material, but we cannot gift it the history that has made these relics what they are today. Their current condition is the product of a marathon, and we are trying to judge our sprint by the same standard. Ultimately, the greatest barrier may not be in the mix, but in the mindset. Translating ancient performance into modern practice requires more than a new formula. It demands a rethinking of our values. It asks us to shift from a paradigm of disposable cost efficiency to one of intergenerational investment. It challenges engineers to work with materials whose behavior is more complex and time-dependent than the uniform products they are trained on. It invites regulators to find ways to certify materials that prove their worth through historical precedent, not just accelerated aging tests. We are not just trying to rediscover a lost substance. We are attempting to reconcile two entirely different philosophies of what it means to build. One asked, how can we create something that will serve our grandchildren's grandchildren? The other often asks, how can we complete this project on budget and by next quarter? Bridging that gap is the true work of replication, a task that goes far beyond the chemistry lab and into the heart of how we view our responsibility to the future. The most enduring homes were not quarried from distant mountains, but lifted directly from the ground beneath the builder's feet. In the blistering deserts of Yemen, a forest of towers rises from the dust, some over 100 feet tall, their facades glowing like honey in the afternoon sun. This is Shibam, a city sculpted from mud. Across the world, in the arid landscapes of the American Southwest, the great pueblos stand as silent, multi-story complexes, their rounded forms echoing the very mesas they are built upon. These are not monuments to scarcity, but to a profound understanding of the most abundant material of all, earth itself. Through two primary techniques, rammed earth and adobe, ancient builders achieved a durability that modern subdivisions can only envy, and they did it with nothing more than soil, water, and human hands. Rammed earth, or pisse, is a process of elegant simplicity. Builders construct a wooden formwork, then layer in a damp mix of earth, clay, sand, and sometimes gravel. This mix is then tamped down, compacted with immense force into a dense, homogeneous wall. Once the form is removed, what remains is a solid mass with the compressive strength of soft stone, ready to dry and cure in the sun. Adobe takes a similar mix, shapes it into uniform bricks, and lets them bake dry before laying them up with a mud mortar. The resulting structures possess two superpowers born from their substance. First is immense thermal mass. Those thick earthen walls absorb the sun's heat all day long, but they release it so slowly that the interior remains cool. Then, as the desert night brings a chill, the stored warmth radiates inward, creating a stable, comfortable climate without a single watt of electricity. This is passive solar design mastered 1,000 years ago. Their second strength is a kind of resilient forgiveness. A well-maintained earthen wall, protected by a sacrificial layer of clay plaster, can survive the rare desert downpour. The surface gets wet, but the water does not penetrate deeply if the plaster is sound. Then, under the returning sun, it simply dries out, returning to its original strength. The key, as with all ancient wisdom, is maintenance and knowledge. The people of Shibam or Taos Pueblo did not build and forget. They maintained their structures as a continuous ritual, replastering walls annually with new layers of mud, a communal act that renewed both the building and the social bonds that held the community together. This is perhaps the most democratic of all ancient material sciences. It required no advanced technology, no rare ingredients, and no specialized guild. It leveraged local knowledge of which soils were right, which clay would bind best, and how to shape a building to shed water. It created architecture that was literally of its place, rising from the site and destined one day to return to it. In an age of complex supply chains and high embodied carbon, these silent towers and pueblos ask a quiet, powerful question. What if the secret to building a lasting community was not in conquering the landscape, but in knowing how to build with it respectfully, intelligently, and from the very soil upon which you stand? A forest was felled to shelter a kingdom. While mortar and stone defined the south, the great halls of northern Europe were held aloft by a different kind of strength, the immense arched ribs of ancient oak. In the heart of London, the hammer-beam roof of Westminster Hall stretches like a frozen canopy, its intricate lattice of timbers installed in the 1390s and still standing without a single interior column to support its vast span. This is not merely woodworking, it is a profound dialogue with a living material. The medieval carpenter began not with a blueprint but with a walk through the woods. He sought not just any oak but the slow-grown heartwood of trees that had stood for centuries. This dense inner wood, rich in natural tannins, was a built-in defense system, repelling the fungi and insects that would devour lesser timber. But the true insight came in the timing of its use. These master builders often worked with green oak, timber that was freshly felled and still full of sap. To the modern eye, this seems a mistake, inviting warping and cracking as the wood dries. Yet the medieval joiner understood this was the secret to a perpetual embrace. They crafted their legendary joints, the mortise and tenon, the dovetail, with exquisite precision, knowing the green timber would shrink and tighten around these connections as it slowly seasoned in place over decades. The joint would not loosen, it would lock itself into an ever tighter grip, the wood itself completing the final act of construction. The roof's design was a symphony of understood forces. The hammer beam structure cleverly transfers the tremendous weight outward and down through a series of short beams, arched braces, and mighty walls, eliminating the need for central supports that would interrupt the great hall below. But perhaps its greatest feat was environmental. The design ensured the timbers were kept in a stable, dry, and well-ventilated void high above the hall's floor. This protected the wood from the moisture and temperature swings that caused decay, allowing it to settle into a state of perfect, suspended animation. The roof of Westminster Hall is a monument to a philosophy of collaboration. The builders did not seek to dominate the oak, to force it into unnatural permanence. Instead, they listened to its nature, its desire to move and season, and they designed a skeleton that invited that movement, turning a potential weakness into the very source of its enduring strength. For over 600 years, those timbers have whispered a truth that stone cannot tell, that the most resilient structure is one designed not just to bear weight, but to accommodate the quiet, persistent life of the materials from which it is born. The quiet chemistry of the Pantheon is finding a powerful echo in the concrete plants of today. Across the globe, materials scientists are not simply admiring these ancient relics from a distance. They are actively reverse engineering their principles to build a new material future. This is not a nostalgic look backward, but a practical, urgent leap forward, fueled by the undeniable evidence that our ancestors knew something profound about making things last. The most promising frontier lies in a class of materials called geopolymer concretes. Instead of relying on the carbon-intensive process of making Portland cement, these mixes use industrial byproducts like fly ash from coal plants or slag from steel production. These waste materials are rich in silica and alumina, the very same reactive compounds found in Roman pozzolana. When activated with an alkaline solution, they undergo a geopolymerization reaction, forming a dense, three-dimensional network that is highly resistant to chemicals, heat, and seawater corrosion. It is a modern industrial loop closing an ancient circle, turning the waste of one process into the durable heart of another, all while slashing carbon emissions by up to 80% compared to ordinary concrete. Simultaneously, the self-healing intelligence of Mayan plaster is being reborn in laboratories. Researchers are now embedding concrete with tiny, dormant bacteria spores or capsules of polymers. When a crack forms and water seeps in, these dormant agents spring to life. The bacteria consume nutrients and produce limestone, effectively gluing the fracture shut from the inside. The polymer capsules rupture and release a healing agent that hardens upon contact with air. This is not science fiction. It is a direct application of an ancient concept, the idea that a material should be able to repair its own minor wounds, dramatically extending its service life and reducing maintenance costs. It is a shift from viewing a crack as a terminal failure to seeing it as a call for the material's built-in immune system to activate. The philosophy of building from locally available, renewable resources is also experiencing a powerful renaissance. The composite logic of wattle and daub is being reimagined with modern biomaterials. Hemp and flax fibers, grown rapidly with minimal water and pesticides, are being used to reinforce plasters and create insulating blocks with excellent thermal and acoustic properties. Even more radical is the exploration of mycelium, the root network of fungi. Grown around agricultural waste in molds, mycelium can form strong, lightweight, and fully compostable building blocks or insulation panels. After a structure's lifespan, these materials can safely return to the earth, completing a biological cycle rather than a linear path to a landfill. This convergence represents a profound full-circle moment in human ingenuity. The goal is no longer to invent a material that simply meets a short-term strength test. The new ambition is to achieve the legendary durability and low environmental footprint of the ancient world while leveraging the precision and scalability of modern manufacturing. It is about creating buildings that are not just shelters but active participants in their environment, capable of self-maintenance, crafted from renewable or recycled streams, and designed from the outset for a long, graceful life. The past is no longer a silent teacher. It has become an active collaborator, whispering the secrets of permanence to those now building the foundations of tomorrow. Our journey through the ancient world's material pantry reveals a treasure trove of wisdom, not locked away in a library, but written in the very substance of the world that still stands around us. These were not accidental discoveries or happy accidents of nature. They were the hard-won fruits of a deep, patient, and empirical engagement with the natural world, a lifelong conversation between human curiosity and the language of stone, clay, fire, and water. The Roman engineer who mixed volcanic ash with seawater, the Ming mason who stirred his rice porridge into lime, the Mayan artisan who tapped the sap of the chukum tree, each was a scientist in their own right, listening intently to the whispers of their local environment and learning to speak back in a dialect of permanence. What emerges from this global tapestry is a powerful, unified philosophy. True durability, it seems, is never the product of a single wonder ingredient. It is a symphony. It is the chemistry of a slow, intelligent reaction, like the centuries-long crystallization within Roman concrete. It is the principle of local adaptation, using what the immediate landscape provides, as seen in the laterite of Yemen or the pine tar of the Vikings. It is the reverence for patient process, allowing lime to mature for a year or mortar to cure with the seasons. And often, it is the profound cultural intent to build for eternity, a spiritual covenant that infused every stone of a cathedral with the care of generations. This ancient approach viewed a building not as a disposable object, but as a living system in partnership with its place. As we now face the monumental challenges of a changing climate and the stark reality of resource depletion, these ancient material stories offer us far more than historical fascination. They provide a vital source of inspiration and, remarkably, tangible recipes for reimagining our own built future. They point toward a path of low-carbon, circular, and deeply resilient construction. The key takeaway is not to abandon our technology, but to enrich it with this older, wiser perspective. We must learn to look forward by looking back, to blend the empirical genius of the past with the precision and scalability of modern innovation. The goal is to create a new legacy, one where our buildings are not burdens on the future, but gifts to it, designed to endure with grace and intelligence. If this exploration of lost engineering has sparked your curiosity, consider subscribing for more deep dives into the hidden secrets of history that continue to shape our world. We would love to hear your thoughts. Which of these ancient materials, from the rust-defying iron to the self-healing plaster, amazed you the most?